All right, one more and you can go to break. So Desert Hot Springs is located about 20 miles north of Palm Springs, surrounded by Joshua Tree National Park and the San Jacinto and San Gregorio Mountains. Although the city was founded in 1941, the region has been inhabited by Native Americans, the Cahuilla, since about 500 BC. These early inhabitants devised many simple techniques for living comfortably in this climate, and we provided us with much inspiration that we used to actually analyze this building. So Bubbling Wells School was opened in 1992. It was designed by locally renowned Palm Springs architect Donald Wexler. A series of single-story buildings, kind of typical of its era, really relying totally on mechanical means for everything for comfort and lighting and heating, and little consideration for water conservation at all at that time. So understanding this particular climate zone, while learning of the lives and the tradition of the Cahuilla, led us to propose these simple 9 steps, appropriate and effective methods for conserving energy and water at this particular site. So it's really important that we start to strike a balance between our comfort and the resources expended. So the first step we took was to understand the resource footprint and the water footprint of the building. So we are projecting that over the next 15 years to 2030 that this building would actually use about 2,580 metric tons of CO2, or emit that much. The project water footprint is 161.9 million gallons of water. So if anybody's curious, this is about what 1 ton of CO2 looks like. And then about 161.9 million gallons of water would fill 245 of these swimming pools. So what we were looking at here is kind of taking our zero net energy approach through these series of steps. And then also we'll look at the water reduction. 25% was our kind of target, but obviously we want to go farther if we can. And then we actually compared this against the OPSC modernization budget, which would be about $5.2 million for this particular project based on their pupil ADA count. So if there's anything other than sand that is abundant here, it's the sun. Desert Hot Springs sees an average of about 330 days of sunshine per year. Making use of the sun for daylighting is logically the most effective way to reduce energy consumption. Tubular daylighting devices have grown more efficient and less costly over the years. Just 4 devices per classroom will eliminate the need for electrical sources of light for the entire school day for 90% of the school year. That's pretty good. Natural light also offers well-documented benefits for the students' health and learning retention, along with existing large view windows and the addition of the tubular daylighting devices. I think the learning potential for the students at Bubbling Wells will be significantly increased from its current state. So by coupling this technology with the LED lightings for the overcast days and the evening use, we can reduce our projected carbon footprint by 31% right off the bat with just 2% of our modernization budget, which is a pretty good ROI at that level. So let's take mass out of thermal mass. Thermal mass is why the rock outcroppings and caves provided the welcome comfort for the Cahuilla tribes. The same principle is in play with trom walls filled with water, 1970s, to absorb and release energy. Now we can utilize this same concept, but of course with a little bit of a modern twist. Bio-phase change material, or bio-PCM, we can practically eliminate the need for air conditioning, even here. Resembling bubble wrap, this material can be laid above existing ceilings or installed in walls, kind of like insulation. It absorbs and redistributes energy, much like traditional thermal mass elements. Desert Hot Springs has an average yearly temperature range from 45 degrees to 105 degrees. These bioliquid pillows, they're filled with liquid, freeze or phase change at about 68 degrees, making it ideal for this environment. This will limit the temperature swing throughout the day in the classrooms to less than 10 degrees throughout the year. So the energy savings from the use of the bio-PCM is 24% of our carbon footprint. So we've already gone over the halfway point. We're on step 2. And the cost for this material is about 9% of our construction budget for 1,200 square feet per classroom. So, but what about those extreme days that we can reach nearly 120 degrees here? Well, evaporative cooling is the earliest known form of air conditioning. It has been traced far back as 2500 BC with the ancient Egyptian cultures. So as we're looking at this, the Adams Hotel in Phoenix, Arizona, which we had an office there, I didn't know about this, first demonstrated swamp cooling, as it was known back then, in 1916, where they draped damp fabrics over the balconies. It kind of came down like curtains, and the air cooled the guests at night. And what's interesting is you can actually do this at home, and it works. I tried it. It's about 8 degrees. So with the installation of BioPCM, the cooling load is substantially reduced. So we can replace the existing 5-ton package units for each of the classrooms with a 1-ton desiccant cooling unit. So these units will primarily run on their economizer cycle only to fuse air into the room to change the BioPCM material. But they also have enough cooling so it can handle those really hot days. So replacing the existing HVAC, it further reduces our carbon footprint now. We're down to a 60% savings, and this was a 5% of our budget now. So, and a lot of these items are things that you would do in a modernization budget anyway. So the windmills in the San Gorgonio Pass supply enough energy to power an average of 300,000 homes, which is pretty much all of the Coachella Valley. They have become iconic sculptural symbols, not only for clean energy, but for welcoming us to the Coachella Valley as well. The average wind speed in Desert Hot Springs is between 5 and 11 miles per hour, with a significant amount of days well above 15 miles an hour and greater. So if you've ever been there, you know that the wind, it definitely makes its presence known. You always know it's windy, especially in the mornings. So we are proposing the installation of 8 vertical axis wind turbines, each with the ability to generate about 10 kilowatt hours per day of electricity. This equates to about 10% of the total energy needs, or enough to operate the general and emergency lights in all 32 classrooms and support spaces for those rare cloudy days and when the school is in use in the evenings. So perhaps one day the wind turbines at this school or these schools can become as iconic as the ones in the past. So collecting energy from the sun, it's kind of fast become probably our most promising source of renewable energy, particularly out here in the Southern California area, in the deserts. The bright, it's ever-present sunshine in this particular area can produce energy from 9 to 12 hours per day. It's making solar collection extremely efficient out here. So building integrated photovoltaic panels. They're intended to replace conventional materials on the buildings, such as the envelope, the roofing, the windows, even the facades. If we're proposing to replace 60% of the existing roof with a thin ply, flexible, integrated PV, it adhesively applied to the roof, similar to other built-up roofing systems. So with the installation of the integrated solar collection approach, it's our final step here, in tandem with our previously proposed measures, we have arrived at a zero net solution for Bubbling Wells Elementary School. But you want to ask the question, can we go someplace farther than that? And that's where it gets interesting. So let's cut out the energy middleman. So conventionally speaking, once electricity is produced, we then convert it from DC current to AC current, and that's so it can travel long distances more effectively. So with on-site generation, there really is no need to transport the electricity. So meanwhile, education has become more and more kind of reliant on battery-powered devices such as computers, tablets, smartphones, LED lighting. All of these require DC, direct current. This means that the AC is then reconverted back to DC via the use of the adapters. So a lot of energy is lost in this translation. The question becomes, can we generate and store the direct current for these uses? And you know, Tesla now offers this large capacity battery storage known as the Powerwall. A dozen of these units can store enough electricity to operate the general and emergency lightings for all the campus when needed, and the educational devices for instruction. And this technology continues to grow and get more efficient because of the competitiveness of the auto industry. So with capturing the sun and the wind, coupled with the ability to store this energy, gives us not only the tools for the net zero school, zero net school energy, but without any reliance on the grid, which I think is our ultimate goal. So, water. Sand, not grass, is native to desert hot springs. So many schools in California are responding to this recent drought and the stricter water mandates. They're opting to replace their grass with artificial turf. Now, due to the intense heat of the sun out here, this is not even remotely a practical solution for these areas. So once again, we looked at our local history and resources to see if we could find a better solution. Seashore paspalum, took me a while to learn that pronunciation. It's a common grass varietal used in much of California. Although originating in Africa, a California hybrid is grown locally in the area in the Coachella Valley and Escondido. So the drought-tolerant Bermuda variety is extremely resilient to high traffic, very hardy for hot, dry climates, and most of all, requires far less water to flourish in this area. So with efficient irrigation, the drip systems that we have, a 15% reduction in the amount of turf on the campus, still keeping some playfield, and replacing the existing turf with the seashore paspalum, the resulting water savings is already 40% of our annual budget. We all know that irrigation takes the most for the water. But let's not stop. We can go farther. So an oasis in the desert. This is a metaphor for finding the unexpected place of comfort and rest. We love camels, everything about it. So water for this region is mainly supplied by recharging the aquifer from the streams shedding water from the snowpack on the San Jacinto and the San Gorgonio Mountains. So mimicking this process, we're proposing to create a campus-wide bioswale system to cleanse the waters and to allow it to temporarily pool along the way, kind of like a natural stream would. And then the California fan palm, it's one of the, one of the only shade sources indigenous to this region, will become the main feature for the new landscape. Grouped together, these palms create a series of oases, providing shade, psychological and physical cooling on the hot days, as well as a unique and fitting outdoor learning environment for students to understand the precious nature of water in the desert. Water collected from the irrigation runoff, the occasional desert storm that runs through, and the gray water from the campus will filter through these streams, providing sufficient water for the oasis to survive on their own. This new landscape palette and filtration system with the reuse of the on-site water will further reduce our water budget now by another 12%. So we're getting there at 52% savings. So what if we could generate water from thin air? Condensation forms on surfaces when the heat emitted at a greater rate than it can evaporate. This phenomenon is most visible in early morning and late evening when the ambient temperature is the most dramatic in the daytime. So based on this concept, there's a company that has developed and is patenting technology capable of capturing water from the air. This is possible when the relative humidity is above 25%. Desert Hot Springs is ideal for this approach with relative humidity averages throughout the year between 52 and 83%. By using the wind to power a series of cooling compressors, creating a heat exchange within this, and we would mimic this model that we're seeing here, which activates humidity condensers, which then produce water. With 8 condenser units, each with a daily capacity of creating between 250 to 400 gallons of water, we can produce and store, on average, 2,600 gallons of water per day. This is enough water to operate our desiccant cooling units that we presented earlier, as well as about 10% of our irrigation budget on the campus. So now we can add water to the on-site generation category of the lead score sheet. So we've explored some innovative concepts for providing a zero net energy solution and reducing our water budget by 62%. More recent advances like the BioPCM and the on-site DC current usage, as well as the water harvesting, they will continue to increase in efficiency and reduce in cost and make them more viable solutions over time. But 60% of our zero net energy solution was achieved with the use of passive measures only, which is where we need to go. All of these solutions are grounded in an understanding of the history and the appreciation for the reality and beauty of the desert environment. The necessity of controlling our carbon emissions has become alarmingly clear to most. The question now is how to reverse this trend in our energy and water consumption and eventually live once again in the harmony with our environments. Times do indeed change. It took more than a generation for students to become digital natives, where they actually grew up with internet devices as part of their reality in their everyday lives. We need to set the course for our next generation of learners through curriculum and life experience to become the generation of conservation natives. Thank you very much.